Imagine you just spent, I don't know, like 3 weeks building this machine learning model. You test it on your laptop and it hits like 95% accuracy.
Ugh, dream scenario.
Right. It's mathematically flawless. You take it to your manager, you're expecting a promotion, and they just look at you and tell you it's completely worthless.
Yeah, that is a very harsh reality check.
It is. And welcome to the deep dive. If you're a graduate student tuning into this, specifically the first part of your machine learning systems course recap, this is absolutely for you. Today, we are looking at why perfectly coded algorithms just totally fail in the real world.
Right, and how the actual ML process begins way before a model is ever trained.
Okay, let's unpack this, because it's wild to me that a working model is worthless.
Well, it's the reality most practitioners face when they leave academia, honestly. A working Jupyter notebook, sitting on your local laptop, it provides absolutely zero business value.
I mean, I'm stuck on that though. If I write a Python script and it perfectly predicts fraud on my test data, isn't the core of the job done?
You'd think so, but no, because your test data is static, right? And the real world is, well, it's messy and it's fast.
Right.
Consider the constraints of a real-time fraud detection system. That model has to ingest streaming data from thousands of transactions at once, process the features, and run a prediction in like milliseconds.
Which a laptop definitely can't do.
Exactly. Plus, user behavior changes over time. We call that data drift. The fraud patterns today won't be the same next month. So, a static model, it can't scale to 1 million users, and it definitely doesn't automatically retrain itself.
The course materials actually use a really great analogy for this. It's the blacksmith versus the factory.
Yeah, I love that one.
Right, like a traditional data science course teaches you to be a blacksmith. You learn the intricate math to forge this one beautiful razor-sharp sword, your one algorithm.
Right, but an ML system is the entire factory.
Yes, you need the conveyor belts, the safety sensors, the distribution network, all of it, just to produce thousands of reliable tools every single day without the whole building catching fire.
And you know, every factory is totally dependent on its raw materials, which for us is big data.
The famous big data.
Yeah, and we have to look at the core system-level challenges here. The 5 V's: volume, velocity, variety, veracity, and value. Because traditional single-server databases, they just collapse when you throw terabytes of unstructured data at them in milliseconds.
So, that myth of the lone genius data scientist,
Oh, it needs to be retired immediately.
yeah, because if you're building a factory, you need a blueprint and a huge team. You've got data engineers laying pipelines, data analysts understanding the history, data scientists prototyping, and then ML engineers handling the actual deployment.
If we connect this to the bigger picture, to manage all that chaos, you really rely on the data analytics lifecycle. It's the blueprint that ensures the factory actually gets built right.
And there are 7 phases to this, right?
Yep. Discovery, data preparation, model planning, model building, communication, deployment, and monitoring. And it is highly iterative, not a straight line at all.
I want to zoom in on that first phase though, discovery, because it feels like a step people just rush through, you know? They just want to get to the coding.
Oh, absolutely. They want to play with the fun algorithms.
But if you skip it, aren't you basically building this highly optimized factory that pumps out the wrong product?
Precisely. Discovery is where you align the tech with the actual business goals. Like, if a business needs to understand why customers are churning so they can change their marketing, they need data analytics.
Because analytics is, like, backward-looking.
Right. It's diagnostic. It explains the past and present. But if you build them a machine learning model instead, which is predictive, you might accurately predict who will churn, but you won't be able to explain why.
So, you solved a really hard problem, just not the one they asked for.
Exactly. You failed the discovery phase.
Okay, so assuming we nailed discovery, phase 2 is data preparation, and I honestly think this is where the war is won or lost.
Without a doubt.
Because if we push raw, contaminated data straight into an algorithm, the math just blows up. So, how do we actually sanitize it?
Well, this is where exploratory data analysis, or EDA, comes in, and it requires immense rigor. You're looking at distributions, running hypothesis testing, calculating confidence intervals.
It sounds exhausting, honestly.
It is, but you're trying to figure out the fundamental shape of your data before an algorithm ever touches it.
If you're studying for the exam right now, I feel like it's tempting to think of EDA as just a technical cleanup step, but it's an investigative process.
Oh, 100%.
Think of it like being a detective at a crime scene. If you walk in and see broken glass on the floor, you don't just sweep it up and pretend the window's fine. You have to ask why the glass is broken.
I love that analogy.
Right. But in data science, people sweep up the glass all the time. They see missing data and they just blindly fill it in with the column average.
Which introduces massive statistical skew. In EDA, we actually categorize missing data into 3 mechanisms. First is missing completely, at random or MCR.
So that's like, if a temperature sensor loses power for 2 seconds because of a random glitch.
Exactly. The missingness has nothing to do with the temperature itself, so in that specific case, filling in the blank with an average makes mathematical sense.
Okay, that makes sense.
But then consider missing not at random, MNAR. Imagine a survey predicting customer value and it asks for annual salary. High-income individuals often refuse to report their salary on these things.
Oh, so the fact that the data is missing is directly tied to how much money they make.
Exactly. So, if you sweep up the glass, if you just blindly fill all those planks with the overall average salary,
You're essentially erasing your high-income demographic.
mathematically erasing them, the model will think they don't exist. And the same logic applies to outliers.
Wait, really? Because usually, we just delete outliers, right?
Well, extreme values are highly context-dependent. If you're building a system for a hospital to detect cardiac events, or a bank detecting fraud, those massive outliers aren't errors. They are the exact anomalies you are trying to catch.
Wow, okay. So by doing rigorous EDA, you predict the whole integrity of the downstream model.
Exactly. You establish trust.
So let's follow that downstream. We've done our EDA, we trust the data, but we hit a roadblock. The data has no labels. We have millions of rows of customer behavior, but no one has neatly categorized them as budget shoppers or luxury buyers.
Ah, right. So we have to transition to unsupervised learning, specifically clustering.
Unclustering is just structure discovery, right?
Yeah.
Grouping things by similarity.
Yes. But the challenge is that an algorithm doesn't know what a customer is. It only understands geometry and distance in a high-dimensional space.
And here is where it gets really tricky. I was looking at the notes on feature scaling, and skipping it seems like a massive trap.
It is fatal to the model.
Because if we want to cluster customers and we use Euclidean distance to compare their age in years to their income in dollars, how does the algorithm even handle those different units?
It doesn't. Euclidean distance just measures a straight line. If customer A and B have an age difference of 20 years and an income difference of $50,000,
the $50,000 just totally crushes the 20.
mathematically, yes. The algorithm clusters entirely on income. Age becomes irrelevant.
Because 50,000 squared is astronomically larger than 20 squared, so you have to standardize and scale everything first.
Right, so the features carry equal geometric weight, and once they're scaled, you have to pick your algorithm. K-means is the classic starting point.
Okay, K-means, that's the one that uses centroids, right?
Yep, it places a predefined number of centroids, K, and iteratively moves them to minimize the within-cluster sum of squares, or WCSS.
I like to think of K-means like a cookie cutter. It stamps out these perfectly compact spherical shapes, no matter what the raw data actually looks like. It's efficient, but it forces your data into circles.
Which is exactly why we need alternatives like DBSCAN. DBSCAN is density-based. It looks for contiguous regions of high data densities, separated by low density.
Sticking with the kitchen analogy, if K-means is a cookie cutter, DBSCAN is like pouring water on a countertop.
Oh, that's a good way to visualize it.
It just flows and takes the exact irregular shape of the puddle. If your data looks like crescent moons, DBSCAN maps it perfectly. K-means would just draw a straight line through the middle and fail.
Plus, DBSCAN explicitly identifies noise. If a point is in a low-density area, it's labeled an outlier. K-means would literally drag its centroid outward and force that outlier into the cluster, messing up the whole group.
And then there's hierarchical clustering, which uses those dendrogram trees, right?
Yes, which is great, because you don't need to predefine the number of clusters. You just slice the tree wherever you need.
But since we don't have an answer key in unsupervised learning, how do we actually evaluate if our clusters are good? Like, if I'm studying right now, I might just memorize the metrics, silhouette score, Kolinsky-Harabaz, but what's the actual intuition?
It all comes down to two tensions, cohesion and separation. You want points inside a cluster tightly packed, that's cohesion. And you want different clusters far apart, that's separation.
So, how does silhouette score measure that?
It compares a point's mean distance to its own cluster against the mean distance to the nearest neighboring cluster. You get a score from -1 to 1. A score near 1 means it's firmly in its cluster.
And near 0 means it's right on the boundary.
Exactly. And Kolinsky-Harabaz uses variance to measure that same tension. It's how you prove your segments are real, not just random artifacts.
Okay, so clustering is great for static entities, like customers. But what if we wanted grouped ordered behaviors over time?
Then we move to association and sequence mining, uncovering hidden rules.
Market basket analysis.
Exactly. Association mining discovers co-occurrence in transactions, like what items are bought together. Sequence mining adds the dimension of time.
Let's dig into market basket, because the metrics are so intuitive. You start with support, which is just popularity, like what percentage of carts have both bread and milk.
Right.
And then confidence is reliability. If you grab bread, what's the mathematical probability you also grab milk? But you can't build a system just on that, right?
No, you absolutely cannot.
Because of universally popular items. Like, if 90% of people buy milk anyway, and you find a rule saying bread drives milk sales with 90% confidence,
Oh,
well, the bread actually had nothing to do with it.
exactly. Which is why lift is the critical metric. Lift corrects for that baseline popularity.
So a lift of 1 means 0 relationship, but greater than 1 means they actually drive each other's sales.
Right. But computing that at a system level is a nightmare. Imagine checking every combo in a database of billions of transactions.
It sounds impossible. So how does the Apriori algorithm actually pull it off?
It uses the anti-monotone principle. If a customer rarely buys apples, you don't need to check if they buy apples and bananas. Apriori instantly prunes millions of useless branches.
That's elegant, but a priori still requires multiple scans of the whole database, right? If it's terabytes of data, that's massive latency.
Which is why FP growth is preferred for production. It only scans the database twice, compressing the data into an FP tree.
By looking for shared prefixes.
Exactly. If 1 million people buy milk, bread, and eggs, it just creates one branch and updates a counter. Vastly more efficient.
And for sequence mining, adding time, we use stuff like GSP and prefix span.
Yep, for tracking weblogs or customer journeys over days or weeks. But this raises an important question.
Which is?
These patterns are useless unless tied to business logic. Dashboards, real-time pipelines, recommendation systems. You aren't doing this for the sake of fun math.
It has to have value. Wow, okay. We have covered a massive amount of ground today. To synthesize this for the exam, what are the core takeaways?
Well, there are really 10 core principles. First, ML is an end-to-end life cycle, not just algorithms.
Right.
Second, analytics explains the past, ML predicts the future. Third, big data requires system-level thinking, those 5 Vs.
Volume, velocity, variety, veracity, value.
Exactly. Fourth, Data prep and ED determine if a model can even be trusted. Fifth, you have to diagnose missing data, outliers, and bias carefully.
Sweep up the glass properly.
Yes. Sixth, the life cycle is wildly iterative. Seventh, clustering finds hidden structure, but it totally depends on your distance metrics and assumptions.
Don't forget to scale those features.
Never forget. Eighth, association finds co-occurrence. Sequence mining finds ordered patterns. Ninth, pattern discovery is only valuable when connected to business decisions.
And the 10th.
Responsible machine learning begins with responsible data understanding.
So, what does this all mean for us as system designers? I want to leave you with this final provocative thought to mull over.
Oh, I like these.
If our unsupervised algorithms clustering, sequence mining are explicitly designed to map the patterns we already naturally create, are we just building systems that predict human behavior? Or by feeding those patterns back to users through automated recommendations, are we building systems that ultimately constrain and shape human behavior into tighter, more predictable loops?
Wow. If the system works perfectly, the line between predicting a choice and engineering a choice completely disappears.
Keep diving deep, and good luck on the exam.